Hi, welcome back to AP Physics C Mechanics Unit 2, Newton's Laws of Motion. So in the last video, we went over a problem-solving strategy of draw, sum, solve. In this video, we're going to look at just some common forces and some example problems. One, applying that draw, sum, solve process, but also these forces that we're about to talk about. Now, this video will not encompass friction. We'll have a separate video on that later in the playlist. But some of the most common forces that are used in these problems. Okay, so the first thing, let me change the color because it's. So the first one is going to be weight. Okay, so one thing to note that this is not mass, but it does come from mass, right? The second thing is this is the force of gravity experienced by an object. So when you go to the doctor's office, they're going to tell you how many pounds you are. That's your weight. So that's how much force you're experiencing at that point, at that given time, due to the earth. If they then flip it over and say, hey, this is your weight, and they give it to you in kilograms, well, that's an incorrect statement because kilograms is our measurement of mass. And to calculate weight is very simple. So F sub g is the variable, all right, and it's just going to be m times g, where in this case, g would be 9.8 meters per second squared. And the other thing is that it always acts downward, okay, because it is the force due to gravity. It is going to be downward, all right, when we draw our free body diagrams. And the weight will exist on every single object that we have. The second common force is what we call the normal force, okay. One thing to note, it's perpendicular to the surface. In fact, in math, if they ask you to draw a normal, you're going to draw a perpendicular line to a line segment. Now, if there is no surface, there is no normal force. Okay, that's one thing to know. A lot of times students will try to force that onto an object that is falling. But the thing is, there is no surface when an object is falling. So there has to be like two surfaces in contact. We call it F sub n, right? So a lot of our variable representations are capital F sub some letter in the K, and that letter directly ties back to what the force is, okay? And then more times, right, in most cases, this normal force will balance the weight. The way you think of it, it's the force that allows objects to stay on surfaces, right? So if my weight was greater than the normal force that could be provided by a table, something would go crashing through the table. Or vice versa, if the normal force provided a value that was greater than the weight, then you couldn't put that object on the table because it would just bounce off, right? Because the normal force would be greater, thus creating, an acceleration in the upward direction. All right. The next one is tension. Okay. Tension exists in cables, ropes, strings, right, or anything of that manner. Okay. It pulls outward along, the two ends of the rope, or cable, strings, whatever. The way you think of it is you can't push a rope, but you can pull a rope. And if you want to know, think about it, think about tendons in the human body. You see that TEN, right? So tendons will undergo tension. And oftentimes tension is something that you calculate. There's no set equation for it, much like there isn't one for normal, but although normal is usually balancing out the weight, so typically the normal force would just be equal to mg. But with tension, it's something that you would have to calculate. You may be, and we're going to do an example with someone walking on a tightrope, okay? And so we have to calculate the tension in the string. And then the last common force, even though there is a more common force of friction, is the spring force. And this occurs when deformed a spring, sorry, I'm reading my notes as I'm writing this, can come back to its original state. So if it doesn't come back to its original state, then there's no more spring force. Okay, there is an equation. So F sub P is going to be negative Kx, and this negative sign makes it is what we call it is a restoring force. So what that means is that it wants to come back to its equilibrium or its 0 point. So anytime that an object is pulled away from that point, it wants to come back to that. And so the spring force will restore back to equilibrium. And that K value is something that we call the spring constant or force constant. Sometimes you see that written on, especially the AP test, and saying, okay. And basically it tells you how stiff a spring is, like how easy or hard it is to stretch, compress. So for example, a slinky would have a very low spring constant because you don't have to apply a lot of force to it to get it to move a meter. Okay. The spring constant is measured in newtons per meter. So that just basically tells you how many newtons per meter you need to stretch, right? So a slinky has a very low K value, whereas a garage door spring has a very high K value. So now let's look at, a couple example problems centered around these common forces. So we're going to look at one that's really involving, you will see, so there is some friction here, but we're not going to dive too much deep into it. But the main thing is the incline plane problem, okay? So we follow our steps, draw, sum, solve. Well, the diagram here already has our draw step, right? So we have a skier going down a slope, mass of 60 kilograms. We want to find what is the friction what is the acceleration if friction is negligible, and then what happens when there is friction involved, okay? Incline planes, what happens is you will want to turn your coordinate system, even though over here it says up the incline. I like to call down the incline my positive, just because it'll keep the idea that if we do have friction, that it'll be in the negative direction. And so there's my draw step. So that puts normal and WY in the vertical, and that puts any friction and WX in the horizontal, right? But note that the weight force here is always straight down. But the reason why we have to break it up into components is because that is the only force that is now in 2 dimensions versus 1 dimension. All right. And so WX, WY, typically it would be cosine goes to X, sine goes to Y. But in this case, because of the angle that we're given or that we know in our diagram, it actually flips the sine and cosine. All right. And so now I'm going to do my XY chart. So part A is going to be no friction. Part B is going to be friction. So sum of the forces in the Y direction is going to be equal to 0. We're not accelerating like this. It's accelerating down the incline. And so we would have normal force minus WY equals 0. And this tells us the normal force is equal to WY, or normal force is equal to mg cosine theta. Now, for this problem, we don't have to worry about that normal force, but I just wanted you to go through and see what the steps were. And so then we have the sum of the forces in the x direction is ma, and then the only force we have in this case in part A is going to be the x component of the weight. Okay, so really this is the sum step, right? SUM. And now we're going to go through and finish up our solving step. We've already kind of done part of it. Now we're going to do the rest of it. So WX is mg sine theta is going to be equal to ma. The m's would cancel, and you would find that acceleration is just simply g sine theta when there's no friction involved. So A is going to be 9.8 sine, and they tell us an angle of 25 degrees. And so A is going to equal 4.15 meters per second squared. So that's the acceleration for part A. Now let's see what happens when we introduce in friction. So the y side, this y, would also be the y side over here. Okay, but again, we don't have to worry about it because they give us the friction. So now instead of just having, sorry, there should be an x. So instead of just having Wx, now we have friction. Okay, and so we would have mg sine theta minus F equals ma. A is going to be mg sine theta minus F over m. You can split this fraction if you want. So you would see this g sine theta minus F over m. Okay, and so we already know what g sine theta is. That's 4.15. And we're going to do 45 divided by 60, because that's her mass, right, with everything. Okay, and so then we're going to do, our answer ends up being 3.4 meters per second squared. So you can see that with acceleration, or with friction, her acceleration does go down, which means she's not accelerated as much as if she had no friction. All right, so let's look at a tension problem. So tension here, we have a tightrope walker. Here's our draw step. So we do have to break TL and TR into components. So we have TLX and TRX, TLY, TRY. Well, the good thing is we don't have to necessarily worry about the X direction on this one, because as long as these angles are the same, right, the X side will just cancel out. So we're just, and because of that same angle, we know that TL is going to equal TR. Okay, and so it would be, we're just going to call it T. So it'd be T sine theta, and then another T sine theta. So again, I don't have to worry about my X direction, because basically you would just find out that TLX and TRX will cancel out, leading to this kind of relationship, right? And so the sum of the forces in the y direction is going to equal 0. And so I'd have T sine theta plus T sine theta minus W equals 0. But remember, this W is what we've called FG in our table. So I have 2T sine theta equals W, and then so T is going to be equal W over 2 sine theta, and that's going to equal 70 times 9.8 divided by sine 5, and you would find that the tension, I'll put it over here, is equal 3.9 times 10 to the 3 newtons, right? And so TL and TR, right, you got basically 3,900 newtons here in each string. Is it 3? I just want to carry. That seems like a little bit of a big number. So 70 times 9.8 divided by sine 5. Make sure I'm in degrees. I am. Yep, and divide that by 2. Yep, so it would be 3,900 newtons. Okay. All right, so in the next video, we're going to now talk about friction, and then we'll do some other forces that are associated with friction.